In this video, we'll look at adding capacitors to our DC circuits. Capacitors are kind of interesting in DC circuits in that they introduce time-dependent circuits, and so we're going to be gradually moving away from steady, constant currents to currents in these circuits that only go in one direction. But they vary with time. So they are direct current, but they're no longer steady, constant currents in general when you put capacitors in the circuit. Well, just to recall, we've got two circuit elements that we've explored in a little more detail. Voltage drop across a resistor. We said as we move across these, we use the general formula delta V for resistors plus or minus I times R. You have to have the direction of the current that's assigned to be positive current flow direction. And then you can mark the polarity because positive charges always move from high potential to low potential. And then depending on which direction you move across that circuit element, you choose the last sign hit. So if you move from left to right, you'd choose the negative sign. If you were going and applying Kirchhoff's voltage law going from B to A, then you'd use the plus sign. Similarly for EMFs, we have a battery here, or a cell, ideal battery if you will, and again the long bar positive, short bar negative, and the delta V across. Depends on the direction you go, but again you just always use the last sign that you hit as you move across it. And the EMF is generally given in volts, so you'd have 12 volts of EMF if this were a 12 volt, so you just put 12 volts in to do that. So we've seen those before. We can do a similar kind of detailed analysis for capacitors. Yeah? And in general, the charge on the capacitor may vary with time. And so I'm going to start using little q for the most part whenever I'm looking at a time-varying charge on the plates. But remember, it's a capacitor, so it has equal and opposite charges on the two plates. I'll indicate this one with positive and this one was negative. And we know that the charge is equal to the capacitance times the potential difference across, so we can solve that for the potential difference across this capacitor in terms of the charge, the magnitude of the charge on the plate divided by C. And now then, we're in a position pretty much like we did before. We can look at going from A to B across this. And remember, delta V A to B is the final minus the initial. And magnitude, the voltage difference across the plates of a capacitor, is the charge on the plate at any given instant divided by the capacitance. And if pretty obviously, if I'm going from high potential to low potential, remember positive charge is not only positive charge, but it's also the high potential, and negative charge is the low potential. And so here I've got VB is this side, which is the low side, so this number is smaller than this number. And so I would get this magnitude, but it has to be negative because I get a potential drop as I go from A to B. Vice versa, as I go from B to A, then I get a potential increase. I'm going from low potential initially to high potential. So VA is the high potential side of this because that's the positive charge, and VB is the low potential side, and so we choose the positive sign there to get the correct sign. And so we get essentially the same rule for capacitors. We have to assign what we're going to call the positive and negative sides of it, and the potential difference from one side to the other is going to be the charge on the capacitor plate, the magnitude of the charge divided by the capacitance, and then plus or minus. And then you simply choose the last sign that you hit as you go from one to the other, one side to the other. Let's give an example, a quick example in this case. I'll assume that we have a piece of circuit in which I've assigned the current flow going in this direction. And notice the current flow, this is all of this is in series, and so the current going through this whole branch is the same. And and we'd like to get the total potential drop from A to B. Again, what I do is I mark the polarities. And the way I kind of look at it is current always goes from high potential to low potential. And so this is the high potential side. Once I've assigned the current flow direction, it's going to have at any given instant a plus Q on it. And this side over here is the low potential side. Another way you can look at it, this current is bringing in positive charge that's being put on this plate. And so this side becomes positive, and then the other, they always have to have equal and opposite signs. We can also likewise mark the polarities of the resistors once I assign the current flow. So capacitors are pretty much like resistors insofar as it's the current flow direction that you're calling the positive flow direction that allows you to assign the polarities. Current always flows from high to low, so this is positive, high side, high potential side, low potential side. Current always flows from high potential, low potential, high potential side to low potential, and so on. And then to get the total voltage drop, you just voltage drop across the resistor, plus or minus IR1. Voltage drop across the capacitor, plus or minus Q over C, the instantaneous charge on it divided by C. And then the voltage drop across R2 is plus or minus IR2. And if you notice, as you move across each one of these in this direction, the way I've assigned things, these are all negative, and so the total voltage drop is a true voltage drop across each element, and so you just sum up all those negative numbers to get the voltage drop. Capacitors are kind of an interesting thing, so let's look at this in just a little bit more of a microscopic detail. There's really a gap in between here, and if it's a good capacitor, there's no real charges that is going from this from the left side of the capacitor, the left capacitor plate over to the right capacitor plate. But what happens is the current that's flowing in this direction is bringing in and putting more and more positive charge on this plate. Well, this side over here is metals. Metals have lots of free electrons that are easily moved, and so this positive charge starts attracting negative charges moving in here and getting over as close as they can to this positive. And so negative charges moving in this direction to fill in this negative plate so that we have this equal and opposite amounts of charge on the plates. Well, negative charges going this direction corresponds to a positive current flow going in the opposite direction. So we get current really on this side, current on this side, with really no flow in between, no current flow in between. And that's how the current essentially flows through a capacitor. Now, I'll often draw it like this, and you'll see people do it, that the current is flowing through this capacitor in this fashion. But again, as you move across, that gives you the polarity, the plus high potential side and the low potential side. And even though we know it doesn't really jump across, it's not having dielectric breakdown and jumping across this central element, we go ahead and draw the current flow in that direction, presumably through the capacitor. Well, with those details, we'll move on to looking at a specific example. We'll save that in the next video in this series.